So in this presentation, we have to talk about the concept of spin. Suppose a dynamical variable is a constant, that dynamical variable should commute with the total Hamiltonian. This is a rule available in classical mechanics. We have to verify this condition in the Dirac case also. For that, start with the Heisenberg representation. In Heisenberg representation, the equation of motion is I h cross d by dt of Lx is equal to Lx comma h. We have presented these two operators in the square bracket, which means that if the x component of orbital angular momentum is a constant, that should commute with the total Hamiltonian. That is Lx h equal to HLx. Now we have to verify the same using our Dirac's Hamiltonian, h equal to c alpha dot p plus beta mc square. Here alpha dot p is expanded as alpha x px plus alpha y py plus alpha z pz, then multiply all the terms by c. Now take this equation I h cross d by dt of Lx, then this is equal to inside the square bracket Lx comma, this is the Hamiltonian value, and align the Hamiltonian into different compartments with Lx. So Lx comma c alpha x px, then Lx comma c alpha ypy plus Lx comma c alpha z pz plus Lx comma beta mc square. Here the first term is concerned, all are expressed in terms of x, so this is equal to 0. You know that the x component of orbital angular momentum is commuting with beta mc square, so this component is also 0. Therefore, the value of I h cross d by dt of Lx equal to Lx comma c alpha ypy plus Lx comma c alpha z pz. We know the value of Lx equal to y pz minus z py. Substitute this value here in equation 2, we can get the equation of this form. Now consider the first term. We have to separate the first term into two terms, y pz comma c alpha ypy, first term, then take this minus sign outside, then zpy c alpha ypy is our second term. In the same manner, separate this into two compartments, y pz comma c alpha z pz minus of zpy comma c alpha z pz, then take out c alpha y from this compartment. See, here also take c alpha y, here take c alpha z, here also take c alpha z. Then we may get c alpha y into y pz comma py minus of c alpha y into zpy comma py plus c alpha z into y pz comma pz minus c alpha z into zpy comma pz. Here the second compartment is having zpy comma py terms. These two terms are expressed in py, so this compartment is 0. See this y pz comma pz, then these two are expressed in pz, so this term is also 0. So the value of I h cross d by dt of Lx equal to c alpha y pz comma py minus of c alpha z zpy comma pz. Consider this formula, ab comma c equal to a into b comma c plus a comma c into b. Say this term is expressed using this formula. This is a, this is b, this is c. So that c alpha y into a outside y, and inside the square bracket b comma c, that is pz comma py, plus inside the square bracket a comma c, so y comma py is present inside the square bracket, and b is present outside. The value of b is pz. Using the same formula, expand this term also, we can get the equation of this form. Here inside the square bracket pz py is present. Pz py are commuting with each other because the z component of momentum commutes with the y component of momentum, so this compartment value equal to 0. In the same manner, the y component of momentum commutes with the z component of momentum, so this component is also 0. So the above equation is modified in this form. say y comma py value is IH cross. Similarly, z comma pz is also IH cross. So this is the way of getting the value of y comma py. Inside the computation, y comma py is equal to y py minus pyy. This is the expansion for this. Py, the y component of momentum operator is h cross by I into dou by dou y. So y into h cross by I into dou by dou y minus of, once again the y component of operator, h cross by I into dou by dou y of y. So this value equal to 0. Dou y by dou y is 1. So the answer is minus h cross by y, that is equal to IH cross. So the value of y comma py is equal to IH cross. Similarly, z comma pz is also IH cross. If you substitute all these values in the above equation, we can get the value of IH cross d by dt of Lx equal to C alpha y into, this term is 0, this is IH cross. So IH cross then Pz minus of C alpha z into this term value Py comma Pz inside the square bracket is equal to 0. Z Pz value is IH cross. So minus C alpha z IH cross into Py. So we had the equation A. See this equation. If Lx is a constant, the differentiation of a constant should be equal to 0. But we are having C alpha y IH cross Pz minus C alpha z IH cross Py. The right hand side not equal to 0, which means that Lx is not a constant. The x component of orbital angular momentum does not commute with the Hamiltonian. Now, let us try with another one operator such that the sum of the proposed operator and the x component of orbital angular momentum should be conserved, and the resultant operator is called the total angular momentum. Clearly, we should understand this concept. We have arrived that Lx is not a constant. Now we are going to add one operator with Lx. Then the addition Lx plus the added operator is equal to constant, we have to prove. So the total term Lx plus added operator is called as total angular momentum. If Lx plus added term is total angular momentum, then the added term should be the spin angular momentum, because the total angular momentum is the sum of orbital and spin angular momenta. In that way, we have to propose an operator. The proposed operator is sigma dash. The value of sigma dash equal to sigma 0, 0, sigma. Once again, start our journey with our equation of motion. IH cross d by dt of sigma x dash is equal to sigma x dash comma h inside the square bracket. Substitute the value of h. Now, align the terms. Sigma x dash C alpha x px, sigma x dash C alpha y py plus sigma x dash C alpha z pz plus sigma x dash beta mc square. If you think about the first square bracket, all the terms are expressed in terms of x, so this value equal to 0. Then sigma x dash beta mc square equal to beta mc square sigma x dash, so this term is also 0. The value of IH cross d by dt of sigma x dash equal to sigma x dash C alpha y py plus sigma x dash C alpha z pz. Here alphas are expressed in sigmas, so that take Cpy outside. Cpy into sigma x dash alpha y plus Cpz into sigma x dash alpha z. But in equation A, we have taken out alpha and p, but here we have to take C and p. Then expand this term, sigma x dash alpha y. This is sigma x dash alpha y minus alpha y sigma x dash. Expansion of this term is sigma x dash alpha z minus alpha z sigma x dash. Here sigma x dash is sigma x 0, 0, sigma x, because the proposed operator sigma dash equal to sigma 0, 0, sigma. So sigma x dash equal to sigma x 0, 0, sigma x. Then alpha y, Pauli spin matrix, Dirac matrix, alpha y equal to 0, sigma y, 0. This is the value of alpha y. Then once again, alpha y equal to 0, sigma y, 0, sigma x dash equal to sigma x 0, 0, sigma x. Plus Cpz into sigma x dash, sigma x 0, 0, sigma x. Alpha z value is 0, sigma z 0. This is also called Dirac matrix. Alpha z is Dirac matrix. We have expressed Dirac matrix alpha z in terms of Pauli spin matrix sigma z. Then minus of alpha z. Alpha z is expressed in terms of sigma z. 0 sigma z, sigma z 0. Then sigma x dash is sigma x 0, 0 sigma x. If you do the multiplication, we can get Cpy into 0 sigma x sigma y 0 minus of 0 sigma y sigma x 0 plus Cpz into 0 sigma x sigma z 0 minus of 0 sigma z sigma x 0. Here the value of sigma x sigma y is I into sigma z. The value of sigma y sigma x is minus I sigma z. Here also sigma x sigma z is minus I sigma y. So that substitute all these values, we can get the final form Cpy into 0 2i sigma z 0 plus Cpz into 0 minus 2i sigma y 0. Here take out 2i outside, 2i Cpy equal to 0 sigma z 0. Here take out minus 2i into Cpz equal to 0 sigma y 0. This is our alpha z. 0 sigma z 0 is our Dirac matrix alpha z. 0 sigma y 0 is our alpha y, Dirac matrix alpha y. Then IH cross d by dt of sigma x dash equal to 2i into Cpy alpha z minus 2i into Cpz alpha y. Then in the above equation, multiply both sides by h cross by 2. We can get IH cross d by dt of h cross by 2 sigma x dash is equal to IH cross Cpy alpha z minus IH cross Cpz alpha y. We can get the equation B. Now, if you are adding equations A and B, the right hand side is equal to 0. The left hand side is IH cross d by dt of Lx plus h cross by 2 into sigma x dash. But the right hand side is 0 because IH cross Cpy alpha z is having positive sign in equation B, whereas in equation A this is having negative sign. The term IH cross Cpz alpha y is having negative sign in equation B, whereas it is having positive sign in equation A. So the right hand side is 0. Now Lx plus half h cross sigma x dash is a constant because differentiation of a constant is equal to 0. If Lx plus half h cross sigma x dash is equal to constant, we know that Lx is the x component of orbital angular momentum, then we can call the total term as total angular momentum. Lx plus half h cross sigma x dash is called as total angular momentum. Then automatically we can point out the quantity half h cross sigma x dash is our x component of spin. From the outlook of sigma dash matrix, we can write sigma x dash square is equal to sigma y dash square equal to sigma z dash square is equal to 1. This provides the eigenvalue of half h cross sigma dash as h cross by 2 and minus h cross by 2. Therefore, the additional part S equal to half h cross sigma dash equal to 1 by 2 h cross sigma 0 0 sigma is called as spin. Therefore, automatically we have arrived at the concept spin from our Dirac's Hamiltonian. Actually, this is Sx. 1 by 2 h cross sigma x dash is called as Sx. 1 by 2 h cross sigma y dash is called Sy. That is y component of spin. 1 by 2 h cross sigma z dash is called z component of spin. That is Sz. In general, S equal to half h cross sigma dash, whereas sigma dash equal to sigma 0 0 sigma. In this way, we have arrived at the concept of spin from our Dirac's Hamiltonian. Then here I have given the hint sigma x into sigma y is called I sigma z. The Pauli spin matrices are sigma x equal to 0 1 1 0, sigma y equal to 0 minus I 0, sigma z equal to 1 0 0 minus 1. Then the Dirac matrices alpha x equal to 0 sigma s sigma is 0, alpha y equal to 0 sigma y 0, alpha z equal to 0 sigma z into 0, sigma z 0. Now we have presented alpha x in 2 by 2 form, but actually the alpha x is expressed in 4 by 4. This is the alpha x matrix: 0 0 0 1, 0 0 1 0, 0 1 0 0, 1 0 0 0. Now we have reduced this 4 by 4 matrix in terms of 2 by 2 using 0 sigma x 0. This compartment is sigma x, this compartment is also sigma x. These 4 elements are treated as 0. These 4 elements are treated as 0. So alpha x, which is 4 by 4 in dimension, is reduced into 2 by 2. 0 sigma x 0. Here sigma x is called Pauli spin matrix. Alpha x is called Dirac's matrix. In this way, we can express the values of alpha y and alpha z also. That's all about the concept of spin.